Now we want to start talking about the photovoltaic technology. All right, we want to start looking at the available technologies that we have, the topologies that we do have. Photovoltaic systems is divided into two. We have the on-grid systems and then we have the off-grid systems. The on-grid systems are usually referred to as grid-connected systems. That simply means that the photovoltaic system is installed and then connected to the utility grid. As you all know, the utility grid for different countries and locations differ, all right? In Nigeria, it is PHCN. In Cyprus, it is called PIPTEC. In other countries, they have different names that they have been called, okay? So if we take Cyprus as an example, it simply means that after installing the photovoltaic power system in your house or in your institution, you connect it to PIPTEC at the end of the day, to the grid, the utility grid. So as you can see here, this is the utility grid being drawn somewhere here. This is the utility grid here being drawn somewhere here. Okay, and then the second configuration we have for photovoltaic systems is the off-grid systems. It is also referred to as standalone systems. Standalone or off-grid because it is not connected to the grid at all. You install it and that is just it. You don't connect it to the grid. In many cases, the standalone systems or the off-grid systems, they incorporate battery. Batteries are incorporated into them as a storage device so that when there is no sun, the device can draw energy that it has stored up in the battery and then continue to supply, make power or energy available to the demand placed on it by the users, okay? Let's take it a step further. The grid-connected PV system, as you can see here, I'm going to point your attention to some important things. What you see here is the PV array. This is the PV array. I'm going to explain to you what an array means. Under normal circumstances, we have solar cells, and then when you put solar cells together, you have what we refer to as solar modules, okay, PV modules. When you put modules together, you have what we refer to as a panel or an array when you put modules together, okay? So this is the PV array, and it could be big, it could be small, depending on the capacity of the PV power plant itself. It's a collection of solar modules. That's what we have here. Now, the energy that is being, the energy that is being provided from the PV array is usually DC energy, because when the sun hits the solar array, the PV modules or the PV array will convert the energy of the sun into DC electrical energy, DC direct current electrical energy, all right? Direct current electrical energy is what comes out of this particular PV array box here. This direct current energy or DC energy then goes through the inverter. What does the inverter do? The inverter converts the DC energy to AC energy. In most of the houses we have today, most of the appliances use AC energy. So while there are still appliances that use DC energy, majority of the appliances use AC energy. In order to ensure that we have AC energy supplied to the user, we must incorporate a grid-connected inverter that converts the DC energy from the array to AC energy. So this equal to like sign that you see here represent DC energy, and this sinusoidal wave you see here represent AC, okay? So it means we are converting DC energy to AC energy by an inverter. When you see this represents an inverter, all right? So the energy that comes out of this inverter is an AC, and then from here, going to the distribution panel, AC energy comes out of this inverter. What enters the inverter is DC. What comes out of the inverter is AC. So what gets into the distribution panel is AC. From the distribution panel of the user, all right? From the distribution panel, the energy is then supplied to the grid. So what goes to the grid goes this way. It goes this way, to the grid. And then from the distribution panel, what goes directly to the user comes this way and then goes directly to the user. It goes directly to the user to supply the AC loads, okay? So this is very important. The grid here for Cyprus will be KIPTEC, for Nigeria it will be PHCN, for your country or several other countries it will be different names that they call the utility grid or utility companies, all right? Now what we have in this entire system here is what we refer to as a balance of system. There is a lot of wiring that goes on here that is incorporated here. There is a lot of wiring that is incorporated here. There is a lot of mounting that goes on here. There is a lot of connections that happen here, configurations that go on in here. Everything put together is what we refer to as balance of system. Then from here, we can take it a step further and try to look at other things that are available in addition to what we've talked about so far. Now, this is a standalone PV system. The configuration is a bit different from the on-grid or grid-connected PV system. Like we have in the grid-connected or on-grid PV system, we have the array here. What comes out of the array is DC energy, okay? The array or the modules convert the energy of the sun to DC electrical energy. It comes out, and then after the solar energy has been converted to DC electrical energy, what happens? In this case, the journey is a little bit different. Since it is off-grid, we don't have a grid-connected inverter here, since it is off-grid. What we do have is a standalone inverter. But before we get to the standalone inverter, two things happen. First of all, we have a charge controller here, and then we also have a battery bank. The function of this battery bank is to store DC electrical energy. That is the function of this battery bank, to store DC electrical energy. And then we also have the controller here, a charge controller here, that regulates the amount of charge that goes in or comes out of the battery, okay? It monitors and checks the battery to ensure that we do not overcharge the battery or we do not overuse the battery. I'm going to be giving you details about the charge controller as we go on, but that's the primary function for now. So from the charge controller, energy is stored on the battery bank, and the energy stored in the battery bank is DC energy that is stored in the battery bank. DC energy is stored in the battery bank, and then from the charge controller, energy goes to the standalone inverter. Not only does energy go to standalone inverter from the charge controller, it also goes directly to DC load. Like we said, this is a standalone PV system, which is off-grid, so we don't have any grid to connect it to. The advantage we have here is that we can supply both DC load and AC load with this particular configuration easily. Before we convert the DC energy to AC energy, we can divert a portion of the DC energy to DC load if we have DC loads that we want to meet. So we divert a portion of it to the DC load, okay? And then we move a portion of the DC electrical energy through the standalone inverter that eventually converts the DC energy to AC electrical energy. So the AC electrical energy goes to the distribution panel, and from the distribution panel, all the AC energy is diverted or moved to the AC load, to the users, and then they can use that to supply their AC loads. This is important for you guys. Please pay attention to it and make sure you understand it. For the grid connected system, we don't have charge controller and then we don't have battery. I'm going to be explaining the function of each of these parts to you in more details as we move on. Now let's talk about the standalone PV system components, and we'll mention some important and vital points about those components. The battery is responsible for storing the excess energy. So this means that when the PV array has converted the energy of the sun, the solar energy, to electrical energy, first, a portion of it will be stored on the battery, and second, a portion of it will be moved to the inverter, the standalone inverter, to convert it to AC. And then a portion of it would also be used directly. So that means 3 places, okay? So the energy from the PV array will go to 3 places. The first place is the battery bank, where the energy, electrical energy is stored. Then the second place is to go to the standalone inverter, where the DC energy is converted to AC energy that is eventually transported to the distribution panel and then to the user's AC load. And third place is to transport DC energy directly to the DC loads so that the user can supply his DC load, his or her DC loads with the energy coming from the PV power plant. So those are 3 places the energy go to. And the battery itself is storage. It stores electrical energy. And the electrical energy stored in the battery is used when there is no sun. When there is no sun and we still have to use the PV, the standalone PV, we collect energy that we have stored in the battery, pass it through the charge controller, then pass through the standalone inverter, convert it to AC, or use it directly with our DC load. Basically, this is very important. In many cases, when a system has a battery, the batteries, depending on the size of the battery, are usually very expensive. They make the system very expensive. So most PVs don't incorporate battery, especially if they can be connected to the grid. There are times when you can combine both the standalone and the grid connected together. You can have the hybrid of standalone and grid connected, put together. So you are connecting into the grid, and then you also have a battery bank. You can have both together. All right. I'm going to explain that to you too as we go ahead. All right, the stored energy can be used when the PV generated power is not enough to meet the load demand. I've talked about that. So in order to ensure that the electrical specifications of the battery are being respected by the rest of the circuit, a charge controller is used, like I explained earlier. So the charge controller ensures that the specifications of the battery are being respected by the rest of the circuit. It ensures that the battery is not overdrawn. It ensures that the battery is also not overcharged. This is very important. Then an inverter is used to convert the DC power into usable AC power for the required application for the AC load that the user would have to make use of. Normally, when we talk about solar PV, where you want to start from is the solar cell. We usually have what we call solar cells. Solar cells are tiny, they are minute, quantities. They are very small, all right? They are very, very, very small. And then when you put many solar cells together, what you come up with is a solar module. Now, when you put many solar modules together, what you come up with is a solar PV array. So a module is an interconnection of solar cells. It is the generic name given to any kind of packaging for an interconnection of solar cells. Irrespective of technology or packaging, an interconnection of solar cells is called a module. So pay attention to that. Now, when we talk about panels, now panels can be defined in 2 ways. When you put modules together, you can also call it solar panel. And then when you put many panels together, you can call that solar array. All right. But in very strict cases, a solar panel can be referred to or can be used when we are talking about a rigid packaging. All right. It can be used when we're talking about a rigid packaging. For example, when we have standard crystalline modules, all right, they are usually called solar panels when they are combined together. A thin film that is flexible, okay, and has flexible laminate is called a solar module because it is flexible, it is not rigid. It doesn't just come in a particular shape that cannot be remodeled, okay? So this is very important, all right? So you can call a flexible packaging, you can call that a panel, you call them modules. And then when you have a more rigid setting, you can call them panels, okay? So we can move from solar cell to solar module to solar panel and then to solar PV array. So here we are going to quickly talk about the current voltage curve of a solar cell. The current voltage curve of a solar cell. What you will find out here is that this is a graph. On this graph, we have the current on the vertical axis and then we have the voltage on the horizontal axis. So you can plot the graph of the current of the solar cell against the voltage of the solar cell. That's what we do have here. Okay, so I'm going to tell you what ISC means. ISC simply means short circuit current. That is what this is called. This is referred to as short circuit current. And then we have VOC. VOC means open circuit voltage. So this is what we refer to as open circuit voltage. Okay, so when we talk about our short circuit current, at that particular point, our voltage is 0. When our voltage is 0, we get our short circuit current. And then when we talk about open circuit voltage, at that point, our current is 0. Pay attention to that. At that point, our current is 0. We have field factor here. What is field factor? Field factor is given as the ratio of maximum obtainable power to the product of open circuit voltage and short circuit current. This is very important. You will see that we have VMPP here. VMPP represents maximum power point voltage. IMPP represents maximum power point current. Maximum power point, it is the point on a power curve that has the highest value of the product of its corresponding voltage and current. So it is the highest voltage possible, that is VMPP. IMPP is the maximum current possible, all right? So multiplying both together gives you the maximum power point. Understand? When you hear the term MPP, it means maximum power point. And it is the point on the power curve that has the highest value of the product of its corresponding voltage and current, or the highest power output, all right? FF represents field factor, and it is the ratio of maximum obtainable power to the product of the open circuit voltage and short circuit current. And that is exactly what we do have here, all right? The open circuit voltage is voltage not connected to any load in a circuit. That means at this particular point, the current is 0. While the short circuit is an electrical circuit that allows current to travel in an unintended path with no or very low electrical impedance. So this leads to excessive amount of current flowing into the circuit. At this particular point, there is no voltage. V is going to be equal to 0. So I short circuit can simply be referred to as the current drawn if load is not present. Current drawn when the voltage is equal to 0. That can be referred to as our I short circuit. All of these parameters are important, and I'm taking my time to show you what they mean, because at some point you will need all of these things. All right. And then we have the efficiency. This is referred to as the rated efficiency of the cell. Rated efficiency of the PV cell, and you can see it is referred to as VMPP divided by the power density. This is power density here. It is the ratio of the maximum power to the input power. PO means initial power, so you can call this input power, while VMPP multiplied by IMPP will give you the maximum power possible, because power is equal to voltage times current. So this gives us the output power divided by the input power. That gives us the rated efficiency of the system. Or you can simply say it is the maximum power point power divided by the input power. So the IV curve explanation continues, but this N here means number of cells connected in parallel. This is what this NX represents. Number of cells connected in parallel, and then this MX represent the number of cells connected in series. You can see we have VOC open circuit voltage here. Here we have our I short circuit current here. And then when we now have many cells connected together, you can see that this value goes up here. When we have many more cells connected together, this value moves to this particular point here. So these represent the number of modules connected in series. This NX represent the number of modules connected in parallel. This is important, okay? We want to quickly look at interconnections of solar cells, the efficiencies of solar cells, and so on and so forth. All right, we have what we refer to as resistive losses in interconnections. We have what we refer to as resistive losses. As a matter of fact, there are several losses when we, in the module, when we connect solar cells together, all right? A single solar cell, we can find its efficiency. And then when we put many solar cells together to make up a solar module, we can also find the efficiency of that module. What you will find out is that here, this is a solar cell. This is a solar cell. This is a solar cell here. This is a connection of solar cells here. This is a connection of solar cells here. This is a connection of solar cells, and this is, you know, collection of solar cells. All of these connections, they make up a module. Okay, they make up a module. Okay, so, and this is a series connection, as you can see, series connection of the cells, series connection of the cells, series connection of the cells, series connection of the cells. All right. So resistive losses in interconnection would mean losses based on some resistance, load resistances, all right? We also have mismatches of interconnected cells. We could have mismatches. Mismatches would mean that when we match cells together that are not of the same configuration, okay? So you have a cell that is not properly matched with another cell. We have what we refer to as mismatches. It could be due to two cells having different capacities. It could be due to two cells. One cell is bad, the other one is good. It could be due to that. So the cell with the lowest current, when you look at it, a cell with the lowest current in the M cells in the series dictates the module current. Now, this is very important for you. When you have three cells put together this way, can you look at it here? We have three cells put together here. If each of these cells are, if one of them is damaged, or if one of them has an issue, or if one of them has a different capacity, and let's say the current here is 2, the current here is 4, and then the current here is 8 amperes, all right? So the current that will come out of these three connections will be the current that is the lowest, which is 2 amperes. That is why we have to be very careful with mismatching solar modules, okay, or solar cells together. When you mismatch solar cells, it is the current that is the cell that has the lowest current that will determine the output of all the cells put together. Imagine you put 10 cells together. All of the 10 cells have 8 amperes, they have good current. And then there is just one cell that has 1 ampere. The entire output of the series connection will be 1 ampere at the end of the day. So that means we have to be careful that we match cells that have the same current together so that we can easily, you know, get the best out of the series connection. The cell with the lowest voltage in the N cells in the parallel dictates the module voltage. Okay, so now that the first explanation I gave you was for the series connection. Now for the parallel connection, the cell that has the lowest voltage will dictate the entire output, the entire voltage that would, you know, be out, that will be given as the output of the parallel connected solar cells. You know, when you have a parallel connection, the voltages are going to be the same, while the currents are going to be different. When you have a series connection, the voltages are going to be different, but the current is going to be the same. All right. So this is the reason you have to be very careful when you are arranging solar cells together in the module, so that you do not have a mismatch. And once you have a mismatch, the efficiencies begin to drop. When the efficiency drops, and then the entire output of the entire module will drop. Okay. And we don't want the output of our module to drop, because we have spent a lot of money buying the modules, trying to, you know, set up a solar panel. So if care is not taken, the whole essence of actually having a solar PV installed will be aborted, will be forfeited, if, you know, we do not pay proper attention to these configurations and matching and mismatching tendencies. Let's go forward. So what are the factors affecting the yield of a PV system? There is an entire topic dedicated to this, but in this case, I'm just going to briefly mention some important factors to you. What you see here is the sun. You can see we have the sun here, and then you can see the sun. This is our solar panel or solar module, okay? So this is the solar module if it is just horizontal. This is the solar module if the tilt angle is this place. This is the solar module if the tilt angle is increased to this particular angle, all right? So you will find out that the output power of any solar module is affected by the tilt angle. Okay, when the module is horizontal, it means there is no tilt angle. The angle of inclination with the horizontal is 0. When the angle is increased a little bit, we have what we have in the middle here. Okay, that simply means that the module would be at the position where it can collect more rays from the sun. All right. So when the angle is increased to a particular angle, which is this big angle we have here, the tilt angle increased, it simply means at this level, you will see that this module is going to collect more radiation from the sun than the other modules will collect. Okay, let us assume that the radiation from the sun is coming like this. It's coming this way, it's coming this way, it's coming this way, it's coming this way, and it's coming this way. What you will find out is that the module that has a proper tilt angle, for example, this kind of high tilt angle for the position of the sun, okay, for the altitude of the sun and for the position of the sun, whether it is during the summer or the winter, you will see that this module will collect more radiation from the sun, and the output of this kind of module will be more. For the one in the middle, you will see that this module in the middle with lower tilt angle, it will lose this ray of the sun, will lose this ray of the sun. If care is not taken, we'll also lose this ray of the sun. We'll only be able to collect this ray, this ray, this ray. If possible, it will also lose this ray of the sun. This one too will not get there. It will go out. It will miss all of these rays. So the efficiency of such a module will be lower than if the tilt angle was properly, designed. And the one that is horizontal will also lose more, rays of the sun, will collect little power from the sun, and then we'll be able to convert just a little, to electrical energy. Tilt angle is a very important factor when it comes to installing solar PVs. And the tilt angle is usually determined depending on the geographical location of the region where you want to install your PV. In many occasions, the standard tilt angle is usually built or designed around the latitude of that region. So that simply means that tilt angle is usually taken as the latitude of that region. Now, there are many more factors that can come into play that can now make the tilt angle of your installation to vary from the latitude by a few degrees, depending on many more factors that I'm going to explain to you when we get to that particular topic. Then also, the orientation is very important. Not only does the tilt angle affect the output of the PV module, the orientation also affects the output of the PV module. Let me quickly give you a definition of tilt angle. A tilt angle is the angle of inclination of a PV module. The angle a PV module makes with the horizontal, The angle a PV module makes with its horizontal is what we refer to as the tilt angle. Now, the orientation talks more about the direction of the PV. All right, is the PV facing south? Is the PV facing north? Is it facing east, or is it facing west? Or is it facing northeast, northwest, east, different directions, okay? We could have different orientations for different kinds of installations, okay? So the orientation talks about the direction of the PV system, while the tilt angle talks about the inclination of the PV system. The standard orientation for optimal performance for a PV system located in the northern hemisphere. North Cyprus is located in the northern hemisphere. So for a PV located in the northern hemisphere, the standard orientation that is used to design such a PV system is the south. If the PV system is facing the south directly, it will get the maximum solar power from the sun and convert that to usable electrical energy for the user. Effect of changes in yearly tilt and azimuth angles on the performance of PV system. Every year and every season of the year experience different variations of the sun, the wind, and climatic conditions. In the summer, we have more sun, very hot sun in the summer. We have cold weather in the winter, and then we have very little time for the sun to shine. And when the sun shines in winter, it's not as hot as it would be if it were to be in the summer. So that would tell you that during the winter, we may not get as much output as possible from our solar photovoltaic power plant. And also during the summer, we can get as much as possible. During the summer, we can get as much power output as possible from our solar photovoltaic power systems. So what usually happens is that during the different seasons of the year, the sun is usually high or low during different times of the year, all right? So depending on whether the sun is high or low, it will determine how we will design our tilt angle. So that means we can have different tilt angles for different seasons of the year for optimal performance of our PV power plant. That's what that simply means. And that is what this particular slide is talking about. This particular screen, that's what it's talking about. So at different seasons of the year, we have different optimal tilt angles to get the best performance from our solar PV plant. However, when you have a small PV plant, a small PV system installed, you can be varying the tilt angles, or you can even install a tracker that would vary the tilt angles, okay, at different times of the seasons of the different seasons of the year and time of the day, right? But when you have a large PV power plant, a large PV system installed, many large PV systems do not incorporate trackers because the cost of tracking systems are usually very expensive. So large systems do not incorporate PV tracker. Large systems usually have fixed tilt angles. Large systems usually have fixed tilt angles. That simply means that it is difficult, it's going to be difficult to be changing the tilt angle at different seasons of the year. You can't just go and be changing the tilt angles. Imagine you have thousands of PV modules on your PV farm. So the cost of actually changing the tilt angle one after the other will be too expensive. If you decide to install a tracker, the cost of doing that too will be too expensive. So in many cases, what happens is that we have a fixed tilt angle for large scale PV systems. This is very important, okay? So that fixed tilt angle has to be an average tilt angle that can actually give us the best performance both in winter and in summer put together. So we will not just use a tilt angle that favors the summer season alone. We will not just use a tilt angle that favors the winter season alone. We will find a midpoint where the tilt angle will favor both the summer season and the winter season during the year. This is very important, all right? The colored cells, the cells are usually of the same color. What they're just trying to tell us is that we could have a mismatch. If we have a mismatch, they're just telling us here that this deep blue cell is different from the sky blue cell. They're telling us that, okay, these are different cells. When you have different cells here, they're going to have different configurations, and then the one with the lowest configuration, especially if they're connected in series, will determine the output of this particular, all the cells in series. The same thing goes here too. I'm just trying to tell you, for example, one of the cells could be damaged and then could have very low current, could be producing very low current, all right? So it could be anyone. One of the cells could have an issue or could, have low capacity, right? And then the output of that particular cell, the current that's flowing through that particular cell will be low. That current is what is going to determine the output. So the colored cells here is just showing that the possibility of mismatches that we can have in the cells. Then someone also asked, is there a machine used to determine the most efficient tilt angle? Yes, like I first of all told you, the tilt angle is usually determined using the latitude of that region. And then, in addition to that, because that cannot be accurate enough, to be more accurate, you can carry out more studies, okay, to find out which one will give you the best tilt angle by using simulation software tools. You could use simulation software tools, and from there you can find out which of the tilt angles is better for different regions. In your software tools, you are going to impute different parameters in the software tool for the region where you want to install your system. And then you can begin to vary the tilt angles. You could use a lower tilt angle, you could use the tilt angle equal to the latitude of that region, you could use the tilt angle higher than the latitude of that region. You keep varying the tilt angles in your simulator, and then you keep checking the output. The one that gives you the maximum output becomes the one that has the optimal tilt angle for that particular region. So you could use simulation software tools to decide, what the tilt angle would be. And then you could also use, historical data, historical performances of PV plants to also determine that. All right. We have come to the end of this lesson. Remember to subscribe to this channel so we can keep this community growing. And don't forget to give this video a thumbs up if you enjoyed it. Don't hesitate to share your thoughts and what you think about this lesson and this video with me and others in the comment section. See you at the next lesson.